Okay. Um, first of all, let's take a look at the development of the technology, and we see that the forms of electronic devices has been changed from the immobile forms to mobile one, and now currently the wearable ones. During this development, the sensor technology plays a very important role here. And so let's first take a look at what the current sensor looks like. Here show the geomagnetic sensor, which is using the digital compass. And if we take a look at the size of the device, we see that the size of the sensor has we're miniaturized. It is very small. And secondly, if we take a look at the block diagram of the sensor parts, the system, and we see that here is the sensor, and then all of the rest of the parts are for the signal processing. So we call such kind of sensor as a smart sensor. And thirdly, we see that the power consumption of such a system is very low. This is because more and more applications have moved to the remote or mobile application forms. So in such a kind of application, the power consumption is very restricted. Here show the flow chart for the sensor, the data information flow chart in the general sensor. And if we want to things related for the in vitro or in vivo monitoring purpose, then we would like the information can be wirelessly transmitted to the end. But we still want to keep this part, the analog signal condition and also the ADC, as close as possible to the sensor. This is because most of the signal emitted from the biological tissue surface is very weak. So we want to keep this part as close as possible to the sensor. Then we can get a higher signal to noise ratio, and also it can get less signal distortion during this long distance or short distance wireless data transmission process. So for in our group, our research purpose is to build such kind of smart sensor system. In such a system, we have the sensors which can handling the signal from the biological surface. And we also fabricated such kind of carbon nanotube-based flexible IC, which can providing the in-situ signal processing capability. So in addition to the properties I mentioned in the last slide, for such a kind of system, additionally, it will be need to be flexible because it will interface with the biological surface. And also, in order to providing such kind of information processing capability, so the electronic devices should be with the high performance. In today's talk, I will talking about some of the most recent progress in my group. It can be, first, I will start with some kind of the sensor research, which is used for the human body monitoring. And secondly, may move to some kind of integrated smart sensor system, which is built on ultrasensitive Fourier. And finally, we're talking about some kind of transferable system, which can just work directly on your body surface. For the sensor, we developed such kind of e-textile. For this kind of textile, we're using two kind of yarns. They can be just woven on the industry sample weaving loom. So that means in this case, all the materials and also the fabrication method of the device, they are compatible with the high throughput textile processing. That's very important. And for such kind of device, we get this kind of fabric, and when it was deformed, and then electrical signal will be generated at each intersection between these two kind of yards due to the triple electrification and electrostatic induction effects. For this kind of fabric, we can just using this fabric to secure around the chest of an individual. And during the respiratory, your chest will just expand and extract. So during this process, we can get there such kind of a signal, and then we can get information about your respiratory rate and also the respiratory depth. And another very important property of such kind of e-textile is that it has such kind of machine wash ability. So you can just throw the device in the machine, and then you can get it washed, and the performance is still acceptable. And to capture the information from the body surface, generally the device should be very soft. So we develop such kind of thermal expandable microspheres-based pressure sensor. It is based on the working mechanism of a triboelectric nanogenerator. In this case, we mixed the thermal expandable microspheres with the PDMS. And when you hit the temperature of the film, then this expandable microspheres will generate such kind of microstructure on the surface. And when the device will experience different level of pressure, then the deformation of this soft structure will be changed. Then we can get a different level of output signal. And in this case, because the device is very soft, so we can get the highest pressure sensitivity achieved in such kind of TNG-based device. And because it is very soft, very sensitive, so when you attach such kind of device on your body surface, then you can get the information about the respiratory rate or your pulse rate information. And we also working on the capacitive sensor-based pressure sensor. In this case, we introduce some the wrinkled structure in the PDMS, which is used as the dielectric in the capacitor. And by adjusting the amplitude and also the wavelength of the microstructure, we can adjust the working range of the sensor and also the sensitivity of the sensor. And when we further introduce some hollows in the micro wrinkles, then we can achieve very, very high sensitivity. So in this case, because the device is very sensitive, so when you attach it on this parts of your body surface, then you can realize the vocalization recognition. It's very interesting about this result. And as we all know that our body surface has a lot of curved surface area. So in order to put the sensor working on such kind of some kind of the hybrid film which incorporating the self nanowires with the paralleling film. And then this film can be conductive, transparent, and it is very stable in the air. And by combining the planar fabrication method and also coated with the kirigami pattern, then we can extend such a system from a planar structure into our deformable 3D sensor platforms. And then we can attach such a deformable sensor system on the curved surface of your body, such as the finger joint or the elbows. Then we can get the in-situ monitor of your body information. And here is about the sensor part. Then we move to the second part. It is integrated smart sensor system on ultrathin foil. And as we know, the mechanical property of your system is highly dependent on the thickness of the integrated system. So when you can get such kind of ultra thin and ultra flexible system, and then you can get a very great conformable contact between your electronic system and the software surface of your tissue or of your body. So in this case, first we achieved some kind of ultra flexible IC, which is constructed based on carbon nanotube thin films. In this case, if we want to directly fabricate the whole system on ultra thin substrate, the fabrication temperature should be controlled below certain degrees. In this case, we're using we record it as doping-free technology by choosing different work function metals. Then we can realize P-type or N-type transistors on such kind of ultra thin substrate at a very low temperature. So we can directly fabricate the circuits on such a ultra thin foil. And after the fabrication, the total thickness of the system could be less than 2 micrometers. And so you can see you can attach such a very ultra thin system on your body. And for the flexible IC, as we want it to handling the signal or handling the signal processing in the system, so it should have very high performance. And in this case, we check the performance of our device, and it shows very high transconductance, which is the highest one achieved for the such kind of device on flexible substrate with the channel length more than 1 micrometers. And such a high transconductance means for the circuit constructed with this kind of a device, it can providing a high signal amplification capability. So it is very useful and very important. And also because the thickness of the system is less than 2 micrometers, so the system is ultra flexible. And when you just bend it, and we say there is no change of the device's performance before and after the mechanical deformation. And as we show that the device has very matched properties between the P-type and N-type transistors. So when we constructed such kind of basic logic gates, the inverter, we see that it can work at very low supply voltage. It can work at 0.2 volts. So that means we see the power consumption of such a system could be very low. And in this case, for inverter, the power consumption could be less than 0.24 nanowatts. So it's low power consumption. And we mentioned that for the sensor, we need such kind of properties. And then how fast this device can operate. We test the speed of our device by using these 3-stage ring oscillators, and it shows that the oscillate frequency can be as high as 5 megahertz. This frequency is high enough to be in the high frequency working range of the RFID technology. So pushing the speed of the circuits to be in such a frequency range is very important for the wireless data transmission in the next step. And then we showed a very interesting demonstration. We get such kind of integrated system. It involving our humidity sensor and also are part of the carbon nanotube-based ring oscillator. And when we attach the system on the body surface, and when we get a different level of switching, then the oscillation frequency of the ring oscillator will be changed. So by this case, we can just convert the analog signal or the information of the analog signal into a frequency information. So it is ready for the next step for the wireless data transmission. In the third part of my talk, we are talking about the transferable system. In the last case, we still have a substrate between the electronic devices and your body surface or your skin. And by using such kind of a transferable system, we can just put all the system directly on your body surface. In this case, by introducing some kind of the sacrificial layer during the fabrication, and then after we got we finish the device fabrication by eliminate the sacrificial layer by a dry etching or wet etching process, then we can transfer all the device or the system we fabricate on the target substrate. We can fabricate the system on a 2-inch wafer scale, and if we check here, we show the carbon nanotube-based device before and after the transfer process. We can clearly say that they are almost the same. So that means the transfer process put minimal effect or effect on the performance of the device. And if we further check the number we achieved here, it shows that we can achieve the ultra-low off-state current, the near ideally switching properties, the SS value, and also we achieved a very large on-off ratio. So altogether, they means that here we achieved the ultra-low power consumption here. And similarly, we check the basic logical gates, the inverters, and we show that in this case, the minimal static power consumption can be as low as 0.25 peak watts here. So the power consumption is well minimized or well reduced. And because we can get a very uniform fabrication device, so we can get more complex circuits, integrated circuits. We realize such kind of full adder, and we show this kind of a biointegration capability. We can transfer the whole system onto the surface of a leaf or onto your body surface, and when the system or when the device on the leaf, we can measure its performance when the leaf was curved, and it shows that it can wear very well when the leaf was bended. So it shows very good biointegration capability. And because it is a transferable method, so when you transfer the whole system to some kind of water-soluble substrate, in such a case, you can get such kind of a transient devices. And we did a very interesting demonstration by integrating some kind of the UV sensor and also a temperature sensor with our device on our water-soluble substrate surface. And then we can get such kind of a transient sensor node. And when we put the or attach such a sensor node on the surface of a plant, and then we can do some kind of this timely monitoring of their plants. We can get their temperature information, we can get their light power, and after the monitoring, then we introducing our artificial rain, and we see that this transient sensor node can be degraded in 90 minutes. So here goes to the summary of my talk, and just here I showed that some of our recent progress for the smart sensor system. We see that we get some kind of the sensor for human body monitoring, and in this case, we would like the sensor should be ultra flexible, should be very soft to capture the information from the body surface. And then we show that for the integrated sensor system, to go with the sensor and also the flexible IC for information processing, we can construct such a system on the ultrathin electronic foil, or we can just get such kind of a transferable system, which can directly on the surface of the biological tissues. And finally, I would like to thanks all my group members who did the great work I just introduced here, and also my great collaborators who makes the research more interesting. And thank you for your attention. And if there's any question, yeah, it's time for a question. Thank you.